Okay. We're gonna begin this class with our first quiz. So I'd like you to clear your desks, take everything off. All you need is a pencil and an eraser. 5 simple questions. Let's make sure that we know the answers. What's Moore's law all about? What's Moore's law all about? Shrinking transistor and feature size in semiconductors, right? So what could we say about Moore's law? What does it predict? Remember, there will be. Yeah, okay, that's, we can do a little better than that. What did Gordon Moore predict about shrinking feature size and the number of transistors in the given area? He said it will double every 2 years. Double every 2 years, okay? All right, okay. Okay, if I'm not mistaken, this is an Alchipon wall. What's a power wall? What's a power wall?
After the rate, we can't speed clock rate because of the power consumption, so we go to multi-cores.
Yeah, you can say that for a given chip, there's a certain amount of power that you can dissipate using heat sinks and fans, and when you get above that, you go to some very expensive cooling, so therefore, you should not exceed that power. What's the main factor in power dissipation, Ur? No, Ur Kumru? Yeah, what's the main factor in power dissipation?
Power consumption.
Power dissipation and consumption, same thing. What's the main factor in that?
Clock rate.
Clock rate, yeah. So therefore, the power wall becomes a clock wall. We can't go so fast because it gives off too much heat. How does that affect processor design? He already said it. If you can't dissipate more power than a certain limit for the chip, and the clock speed's the main, so that makes a limit on the clock speed, and you can't increase your performance unless, what? Unless you change the architecture. And at the same clock speed, you're doing more processing in parallel. Good way to do that is multi-core. It's not the only way, but it's a good way to do that, right? So the power wall is about how much heat to get out of a chip, because the power that goes in gets dissipated as heat. So consumption or dissipation, same idea. How much does the chip consume? That's how much it must dissipate. And if everybody's ever touched a hot light bulb that's been on for a long time, you know that it doesn't dissipate heat very well because it's a vacuum and it's glass, and so the surface temperature is very high. Okay? Now the problem with surface temperatures being high in a semiconductor chip is what? What's wrong with letting the semiconductor run to 500 degrees centigrade, 1,000 degrees centigrade? Let it get hot, Olson. And what's the problem? Bizene. You know, you're not going to touch it. I don't know anybody that reaches into a running computer and puts their hand on the processor. What's the problem?
Very much energy for coolers.
Yeah, but we have lots of things in our life that are 500 watt things. 100 watt is nothing. Your house is full of 100 watt light bulbs. So why not fill with 500 watt processors or 1,000 watt processors? What's the problem? Why is 100 the limit? Yes, when the surface temperature in the silicon goes up, the transistors don't behave. They don't behave. They don't switch right. Yeah, so you don't get the model of switching behavior if you heat the semiconductor up too much. The only way to not heat it up too much is what? Get the heat out.
That gets more strong, the transistor, instead of
Okay, right, instead of beach sand, let's make them from exotic materials that cost 1,000 times as much. Yeah, and that's not going to work. It's a lot cheaper just to say, that's the limit, my friends. Actually, cheaper solutions instead of exotic materials, which still behave as semiconductor switches, are heat solutions. Try to get the heat out. You can bet that all the mechanical engineers know that heat dissipation from hot electronics is a real hot topic. In fact, there's a talk being given this week at Bilkent University from somebody in our own, I think, or maybe it's a guest in our own mechanical engineering department about heat flow. Heat flow is one of the key things in mechanical engineering, and one of the key, special, important areas is semiconductor heat flow. Get it out. Inexpensively. Right now, heat sinks and fans are about the only cheap way. Everything else moves up really expensive above that. I told you about my friend that works for an exotic heat company that makes heat pipes, and they sell them for in the thousands, you know, to military electronics that have to get the heat out and have to dissipate it. Anyway, that's enough on Powerwall. What are the major classes of computer, starting from the highest performance moving down to the lowest performance? What's the top class of computer? Supercomputer. What's the next one down from that? Servers. What's the next one down from that? Personal computers. What's the next one down from that? Embedded computers. Great. All right, that's a pretty easy question. All right. Okay, that's all the hard questions that I asked from Chapter 1. Now let's move to Chapter 2. We've done 2 times The introduction to chapter 2. First Typhoon did it, then I did it. So surely, surely, surely you know lots about the early part of chapter 2. What are the three main formats for MIPS instructions? R format, I format, J format. Three simple classes of instructions. Nothing big there. All right, final question. In a load store architecture, memory operands, in a load store architecture, memory operands, What's a memory operand? It means it's in memory, and it's an operand. What does operand mean? You're going to do an operation on the operand. Yani, 2 plus 2. 2 is an operand, 2 is an operand. Plus is the operator. So a memory operand means for an operation, the memory contains one of the operands. And so you complete the sentence by saying, in a load store architecture, memory operands do not exist. Memory operands are impossible. We only have register operands. I made that point very clear in the last lecture. Memory operands do not exist. We don't have them. You know, that's why it's called a load store architecture. If you need them, you load them in first into register, and then you have a register operand. Okay, so that question was a little on the tricky side, but it required knowledge that memory operands do exist in some other architectures, including the Intel architecture, but they cause it to be slow. So register operands are obviously much, much faster. You don't have to reach all over to memory and get something from a long distance away. You have them locally right there in registers. Okay? All right. Good luck on the next quiz. Study up. Some of you left it blank. I'm so sorry about that. Okay, here we go. Okay, time to move into new material. We're in the middle now. We're in the middle now of chapter 2. Chapter 2 has 3 sections of slides. We're in the second section of slides, okay? We've covered the first section twice. We won't have that luxury anymore, I'm sure you know. All right, let's begin now, continuing our survey through the MIPS instruction set and the instruction set architecture, which are almost the same thing. Okay, conditional operations allow us to change control, to do something if a condition is met, all right? So we will branch to the labeled instruction if the condition is met. Otherwise, we'll just continue sequentially. In other words, do this, here's a branch, a conditional branch, which means maybe we'll do this, or maybe we'll branch and go somewhere else. That's the idea. The flow of control forks here according to the condition. A simple way to, simple way to draw that, simply this. Do this, do this, do this. Make a test. If the test is true, do this, do this, do this. If the test is false, do this, do this, do this. In other words, it's a branch or a flow of control change. All right, let's have a look here. We have in the MIPS architecture, branch if equal, BEQ. It tests these two registers. If their values are equal, then we branch to location L1, which is a label indicating where else in the code to go. If RS equals RT, branch to the instruction at label L1. We have the inverse of that, branch not equal, which says if these two are equal, continue and don't branch, but if they're different in value, take the branch and go to location L1. So branch if equal, branch if not equal. Those are two different conditional branches. And then there's a branch which is unconditional. It's labeled with J, it's a jump. Generally the word jump means unconditional branch, which means from here, go to L1. Always. Not splitting, but just from here, change control and go to L1. So we have an unconditional branch and two conditional branches. One based on equality of operands, one based on inequality of operands. Are there any questions about these? Okay, I think we already have seen lots of examples of register names and register numbers. So that's what will be here for RS and RT. A name or a number of a register in the 32 registers that we have. So we can't use memory operands. We can't compare a memory value to a register value because this is a load store architecture. If you have it in memory, you first bring it in with a load, then use it. This is new. This says that instructions have labels or addresses and that the next one after this one won't be here. Instead, we'll go to the place labeled L1. So we'll see some code that looks like that in just a minute. All right, so that means that we have the ability to do if statements in a high-level language. If else, case, switch, all those kind of things now become possible. High-level languages have structures that need to be supported by low-level language structures. So here we go. If the C code looks like this, if I equals J, do this addition and change f, else do this subtraction and change f. You can see that what I'm going to do here is test I equals j, and if it's true, then we go to the statement that does the addition. That's supposed to say equals. If it's false, we go to the statement that does the subtraction. So here's my else. Okay? So that's the code in C. And so now we're going to have f, g, and h in S0, S1, S2. Okay? Matching, of course, high-level variable names to low-level physical locations. You notice that f and g and h are sort of abstract because they don't really say where they are. They're a name, a label about a value. The value could be in memory. The value could be in register. The value could be on the disk. They don't really physically tie themselves to anywhere. Do you notice that? It's the first thing about high-level language variables. Until now, all the C and Java that you've written didn't say anything about where the variable has to be located. But we have a real machine. We don't have an abstract machine anymore. So in our real machine, every storage value is either in register storage, cache, which is part of the memory hierarchy, main memory itself, hard disk, offline on a CD or a tape, but it's somewhere. It's somewhere. If it's stored, it has to have a physical location. It can't just be hanging around in the air the way that it does in C and Java and other high-level languages. That's the difference. High-level languages are not tied to a machine. Remember, they're machine independent, which means you're not committing to where it's stored. But we are. We're going to commit to F being in register S0, G being in register S1, H being in register S2. That's a very strong commitment. That's called binding. That's when you've placed values in physical locations. Okay? All right, just having said that, I just want to make that connection because it's not made in the book or the slides. Now, let's compile the MIPS code. So the first thing is the test. If they're equal, the compiled MIPS code actually finds that testing the opposite is more effective. So we're going to test if they're not equal. So obviously, if they're not equal, we want to go do the else. So if S3 and S4, which are supposed to be I and J, I'm sorry, I didn't mention those, F, G, H, I, J. S3 and S4 are not equal, we go to else. Does everybody agree that if they're not equal, we should go to else? Does everybody agree that at else, we should do a subtraction? Yeah, okay. So at the label else, we do a subtraction of the S1 and S2 values, which are going to be G and H, and we put the result into S0, which is going to be F. Yes, that's exactly right. That's F equals G minus H. That's F, that's G, that's H. And we say subtract them. So at else, we do that. And after that, what do? Keep on going. So after that, yeah, keep on going to this place here, whatever comes next. So they split, and then they rejoin. And that's what happens in C code, too. After you do this or this, then they both continue with whatever the next statement is. That's what we need to do here in assembly as well. So far, so good? All right, now let's look at the other branch. If they turn out to be equal, it means you failed this test, because this is a test for not equality. If you pass the test, you branch to location else. But if you fail the test, what do? You continue the code. And so if we find that they're equal, by failing the test, we should do an addition. So we want to add G and H, so that's S1, S2, added together, and the result put in S0. And then after that, what do we want to do? We want to go to else. Well, we're going to jump over the subtraction, so we put in a J to, not else, exit, excuse me. So we want to jump to exit. So what we want to do, as you can see here, is either skip over the addition and the jump and do subtraction and continue, or else do the addition and the jump, which skips over the subtraction and continue. So one way has addition and a jump over the subtraction. The other way has a branch over the addition and jump and does the subtraction. In either case, the arrows meet and we continue here. All right. That's your first example of compiling a high-level language control structure into a low-level language control structure. If-else has been done here. We can reduce it to just if and make a smaller one. Okay. We could think about how you would do case switch. Case switch, one way, is just nested if-elses, isn't it? Yeah, you know, if this, do that, else. If this, do that, else. If not any of those, do this, and so on. So you could have a nesting of if-elses. And all that would mean is, if you pass, do this. If you don't pass, have another branch and do that. If you don't pass, have another branch. So you can imagine a chain of branches, each of which says, if I pass, then do that one thing and go to the end, else keep testing. You could organize a case switch like that. That's one way to do it. There's better ways. We'll see better ways. But is that clear enough? If else, and case switch now all have a possible way to be implemented in low-level language simply by having conditional branching. Now the second thing to notice is we tested equality in the high-level language, but we found that the compiler prefers to test inequality at the low level. And I'm just going to leave you with a question to scratch your head and maybe ask on the next quiz, why is that better? Why is that done like that? Wouldn't it be possible to put BEQ here? It would. Okay, so then what's going on there? No, I'm not going to answer the question. I'm just going to put it out to you as a thought provoker for everybody here. I'm glad you're already thinking and have got some idea. Maybe you'll need to help your friends down in Mozart to figure it out too. But before you come back next time, I would like everyone to be prepared with the answer to that question. Why is it better to take the opposite sense in the low-level language? If this was inequality, then we would have BEQ here. If this is equality, we have BNE. Why? That's your question. That's your homework question, okay? All right. Now, you can see that there's an address calculation needed here and here because we both branch to else and jump to exit. So these need to have numbers in order to put those numbers in the instruction. These are alphabetic characters for us to be able to understand, but the machine, of course, needs binary. So we're going to have an assembler calculating an address of else and putting that here, and calculating an address of exit and putting that here. So we can jump to a number and branch to a number, okay? Of course, machines don't deal with ASCII characters in any way, sense, or form. Any questions about this slide? Pretty important. Pretty important. We're jumping right into the good stuff, but you have to understand the relation between the high-level language structures you understand and the low-level language which you are beginning to understand. So we do it by building connections, one structure at a time. Okay, let's move on. Now let's imagine that we want to do a loop. High-level languages have very powerful structures for looping. In fact, often they have multiple loop structures. For, while, until, do while, all kinds of structures for looping. Every flavor and kind. We have to be able to implement those in low-level language. What have we got for our Malzeme? We've got an unconditional jump, and we've got a conditional branch. You think we can do looping with those? Jumping could take me back to the top or out, and the unconditional branch could be test and go out or test and go in at the top, or it could be at the bottom. Now that I've done it, test and what? Go back or keep going forward. Sure. With the structures we have, simply a test box for conditional change of control and an unconditional you will go there now, we can do it. Okay? That's all we need. So we have the structures. Here's a simple loop. While the value of save, the ith value of array save, I'll say it that way, is equal to k, increase I, and keep doing it, and that's all we do. So all we're doing is changing the loop control variable, and that's all there is. Except we're not actually testing the loop control variable. We're using it to access an array, get a value, and see if that value from the array is equal to the value that I'm testing it against. We're trying to find if all values of the array are equal to k. When will we leave this? When we leave this loop? The first time we find an array value that isn't equal to k. So if they've all been zeroed, or if they've all been set to the constant you want, check them all. Uh-oh, here's one that's wrong. Now it's time to go and do something. So you find the first non-k value in the array save. That's the purpose of this code. Okay, let's see how it would be compiled into MIPS code. Hand compiled. Yeah, and we're going to do it ourselves. Obviously, compilers will do this automatically, but you need to understand what's behind the curtain in a compiler. So we're going to understand these compilations ourselves. Okay, there's a thing called loop, a label. And the last thing in the loop is jump back to the top. So we know from that it's not a bottom-tested loop, it's a top-tested loop. And sure enough, we're not quite top. We're shifting, we're adding, we're loading in a word, and then we're branching right here. And we either branch to exit and get out, or we do an addition and jump back to the top. Okay? I guess middle tested is a better way to call this loop. It's not tested technically at the top or the bottom, it's middle tested. Okay, so let's see how it does. Obviously, we've got to first bring in the value for save and compare it to k. So here must be the comparison. And if they're not equal, you go out. That's what we want to do here too. If they're not equal, go out. All right, if they're equal, then we're going to increment S3 by 1 and go back to the top. What's S3? Oh, S3 is I, yeah. If they're equal, you increment by 1 and do it again, and you don't leave the loop. So that makes sense. So test if they're equal. branch, either increment I and go back, or else you went out. What are we doing before that? What's all this work? What's all that? It must be getting this in from memory and getting it ready to compare with that. Let's see what happens. We take S3 and we shift it left, logically, 2 places. What happens if I'm, from your perspective, I'm here and I'm shifted left 1, 2 places? What happens to where I was? We stick in zeros, don't we? It's a logical shift. So suddenly my bit position is 2 places to the left, and where I was is filled with 0. What do? Multiplied by 4. We multiplied by 4, didn't we? Can anybody think why multiplying I, which is an integer index into an array in the C language, by 4 would be necessary at the assembly language level? The hint was given in the last lecture. Why do indices, which are integer at the high level, need to be multiplied by 4 to calculate with them at the low level? Because they are indexes of words, but we deal with bytes. Memory's bytes for us. We don't know anything about how many bytes in a word. Well, we know. We know there's 4, so therefore that's why we multiply by 4. Yeah. So I's value gets multiplied by 4, and we use that in T1. Great. What do we do with T1? We add T1 to S6. What's S6? The address of the save structure's base address. So the beginning, S6, contains what? What does it contain? Save square bracket 0. But we want save square bracket I. So we take our I, multiply it by 4, add it to the base address, and what's here now? The address of the item we want. Yeah, in that T1. And then we take that T1 as an address, and we use it, as you can see, as a memory address to go get its data, adding 0, because it's the perfect thing. We don't need to change it. It's got what we need. Go get it and load it in to T0. So now T0 contains what? This. S5 contains what? K. You're testing equality of this and this. It took 1, 2, 3 steps to get this from memory. Calculate the I, figure it out, add it, bring it in, load it. Now we have it. Once it's in register, the rest is very simple. If they're equal, leave. If they're not equal, add 1 to S3, go back and do the whole thing again. All right. That was quite a lot. 1, 2, 3, 4, 5, 6 lines of code in a new language that you're just beginning to learn. Do you understand it? Do you have any questions about it? Here's one. Okay.
I don't understand the second add.
The second add. The immediate add. Okay. The first add. This one here. Okay. All right. Let's see what's being done here. T1 contains I times 4. So if I is 3, it's going to contain 12. Okay. So we're going to add 12 bytes to the address of the beginning of the data structure. So the beginning address plus 12 gives me structure member number 3. There's save 3. If I want to get save 8, what should I add to the value of S6? 32. Yeah, exactly. If I want to get save 0, what should I add to the value of S6? Okay, I'm asking this. What is the address of that? S6, good. So what is the address of that? S6 plus 40. Do we all understand this? We're having a conversation, but I hope you're all paying attention. This is a really tricky point, and every year students have trouble with it. What is the address of save 3? Yeah, because this is held in S6. Yeah, I need the address, not the value. Look, I better do it this way. Address of that, address of that, address of that. I don't know what the values are. The values are something in memory. But the address is what I need in order to get the value. Everybody understand that with this one, it says, go get the value. Put the value here. And it says, this is the address in memory of the value. When you see that parentheses, it's telling you I'm going to memory, and I don't know what the value is, but you have to tell me the address. If you give me the address, I'll go find the house, knock on the door, and say, whoever's in this house is coming with me. That's what the police do when they arrest you, okay? They come to your address. This is it. Cup of 14. Okay, knock, knock. Open the door. You guys are all under arrest. Or maybe it's William Sawyer. You're under arrest. Or whoever's there, you know, they have a warrant, and they take you down. But they first find the address, and whatever's there, they usually have a search warrant, too. They search for evidence of a crime, right? That's what we're doing here. We're going to the address. That's the door number. We had to calculate it first. Okay, and then we're saying, whoever's there, you're coming with me, and I'm putting you in the processor and register T0. Yeah?
How do we show the array in the array? Like, we show the index of one array with other array.
Okay. I'm not prepared at this early stage in this course to go into complicated. You want an array of arrays. That's what you want, yeah. I think I better not go there right now. We have a class of 50 people here, and I think most of them are really struggling just to get this, and so I don't want to complicate it by adding that degree. Why don't you come during my office hour or during the break or after class, and we could talk about that. I'll be happy to answer the question, but I don't want to make things worse. I want to make things better. We're moving toward understanding of simple, and usually I've learned in teaching, you throw in something really complicated and hard right at the beginning, and everybody goes, oh, you know, and we lose it. Psychologically, it's not good if I answer that question out loud right now to everybody. I'm glad you're curious. No, I am glad you're curious. I'm glad you asked. I just don't want to make things worse for the majority here. Okay, so he's asking, how does memory locate complicated data structures like trees and arrays of arrays and linked lists and things like that? That's a great question to ask. You've just been all in CS-201 and now you're in 202. Surely that should be, I was talking earlier about linking, remember, the abstract to the physical. I talked about little, so he's got a great question. How do I link a complicated abstract structure? You did a simple one, Hoja, but help us with more complicated ones. But, yavaş yavaş, her say adım adım. Tamam mı? Okay.
Sir, I have a question.
Oh, yeah, sure.
Load word in the load word line.
Mm-hmm.
After the ST0, what's the 0 for the memory? For the RAM?
Okay. All right, that's about the syntax of the instruction, right? Okay, so here we go. Load word is the command. We have to have a register here, which we're going to, it's the T register. So that's the destination. And then we have the following. Offset, parentheses, the source register, okay? In this case, the offset is 0. In this case, the source register is T1. And in this case, the destination register, watch this. You know, I'm going to call it the destination register. I hope everyone remembers that RD is the destination for R-type, but for I-type, RT is the destination register. RS and RT are source registers, whoops, for the R-type. But, so let's do it here. Destination, it's that, or in this case, RT. And then for source, we got two sources. For R, it's those two. But for I-type, there's only a single source. And so it's going to be RS. Is that clear? Okay, so that's the syntax of our two types. In J-type, we don't have any registers anyway. So I'm dealing with an I-type instruction here. My source is going to be RS, and my destination is going to be RT. So there's my source. What do I use the source for? What's it used for here? What am I using this RS for in this instruction? What's its purpose? Do I get the data from RS? No, I don't get the data from RS. What do I get from RS? In this case, T1. Well, yeah, the address. I'm using it for address calculation. Tell me, is T1 the entire address? I better not ask that. Is RS the entire address? That's the question I want to ask. Is RS the entire address? The answer is no, it's not. It's part of the address calculation. Now, I'm going to ask you to answer your own question. Tell me what the address calculation is. I want you to look in here. No, don't look at that. Look at this. What's the address calculation? Okay, so he doesn't know. Somebody help him out. What's the address calculation?
If you have address and
Not if we have an address. We're trying to calculate an address. So how do I calculate the address? Yanni?
put offset place an integer and add the original address.
What's the original? We need to make original address. We're trying to calculate an address. And I'm asking you about how the calculation is made. Yeah, there we go. RS plus offset. Okay? But understand that this means the value in RS, because it's not the number of the register, it's the value contained. So we add this register's current value to this offset's amount. Okay, so now let's go back over here. In this case, the offset is 0. So we're adding the value in T1, which we took the trouble to calculate here, plus 0. Okay?
Do we always add with 0?
No, sometimes we add with 5 and 28 and 1,457 and 28 million, and we add with whatever we need. We add with whatever we need. In this case, we need 0, so we add with 0.
Oh, okay, because we calculated earlier the address of the T1, address of the source. So
there's nothing left to add. Yeah, there's nothing left to add. But in some calculations, there will be something left to add.
Why didn't we just? Okay.
Why didn't we?
Okay.
Because the format is.
I'm thinking high level.
I don't know what you're thinking, but the format is you got to write LW, then you have to write a register, then you have to write a comma, then you write the offset, even if it's 0, then you write a parentheses, then you write another register, then you close with a parentheses. That's the format. And you know how high-level languages work. They're very picky. If you don't obey the format perfectly, what do? Guess what low-level languages do? Same thing. They're very picky. Syntax is just a problem, okay? You know, these are formal languages, Beecham cell deal there. In a Beecham cell deal, the only way to survive is to have a syntax that is very rigid. Okay, we speak Turkish and English, and some of you maybe took German and Chinese. Those are lovely. You can write poetry. You can do all kind of weird and strange things to the language. Syntax, great, but those are Dual-Dil. These are Beecham cell deal. You cannot do that. So therefore, please, Lutfen, follow the syntax, okay? So this is part of the syntax right here, is the offset, even if it's 0, okay? All right. Any other questions? Okay. Yes?
Our offsets can be
Negative or positive? No?
I mean,
Can they be variable offsets?
Not intermediate values. I mean, intermediate, sorry. I mean, can we put something like that, $T1 instead of offset?
Let's go to the format. I-type format. What do we got here? Opcode. 6 bits. Then I have 2 things that are 5 bits. What are those? RS, RT. Then I have something that's 16 bits. And what goes here? What goes here? We're discussing the I-type format. Opcode 6 bits, RS 5 bits, RT 5 bits. Now you search this, and you tell me which one is the opcode. Done. Which one is the RS register? Done. Which one is the RT register? Done. What's left? Offset. Where's it going to go? Here. How many bits have I got? 16. What can I do with 16 bits? I can write a number. So this is okay. That's it. So now he wants to put something weird and fancy here, and my answer to you is sorry. Negative max integer done. Exibir akadar, sifr dahil, bir dahil, positive integer akadar. Integer seçeneğiniz budur. Başka bir seçeneğiniz yok. I mean, yeah, that's it. That's just the way it is. No floating point numbers, no array of arrays, no expeditions to Mars or undersea, you know, things or microscopic values. It's got to be an integer from the array from min int to max int. Nothing else. That's the syntax. It's a Beecham cell deal, my friend. Beecham cell. Syntax is rigid. Okay. All right. Anything else? All right. Sorry about that. Okay. Let's take a break. 10-minute break. Come back.